Welcome to the second full lecture of our College Algebra class. My name is Paul Walcher, I'm your instructor, and we're going to be looking at P2 today. I'm going to break this lecture up into several parts, just to keep the videos from being too long. In this first part, we're going to deal with real numbers, and I anticipate probably 2 more videos where we look at the properties of real numbers, and then also look at some exercises. So first, we're going to go through some theory. The first thing you do in most mathematical courses is look at the set of numbers you're going to use throughout the semester. And College Algebra is no different. We will use real numbers throughout the entire semester. We may get some extra numbers later, about halfway through, but we are going to be using real numbers throughout. And the way we're going to do this is that we are going to build up this entire set. So we are going to start off with the natural numbers. Natural numbers are baby's first numbers. They're the first numbers you learn as a mathematician in your mathematical studies. So they are the counting numbers. 1, 2, 3, 4, 5. Literally just count them off on your hand. As we go, I'm going to try and keep up some different notations. Here's the set notation with set brackets on the end, as you can see there. And then on the number line, it will look like this with tick marks, and it's going to infinity on the right. Then going up to the next set, we have the integers. Well, extending the integers from the natural numbers, all we really do is we take the natural numbers, starting at 1, add 0, and all the opposites, all the negatives of the natural numbers. Then on the number line, well, that's a fairly easy flip to make. Now we have all of these tick marks taken care of, going infinitely in both directions. But obviously that's not all of the numbers on the number line. We have all of these gaps in between the integers. So what numbers go in those places? Well, there we start looking at the rational numbers. Because, oh, and I forgot this little note at the end. It is true, if you look at that, the natural numbers are nested or contained within the integers. That'll be true for a few levels of this. So rational numbers, can't really write out using the bracket notation. If you wanted to use a set notation, you could probably take this condition here. This is how rational numbers are usually described. Any number r that can be written as r equals m over n. Basically, any number you can express as a fraction of integers. A fraction with an integer on the top and an integer on the bottom. So here are some examples. 3 over 4, negative 27 over 22, integer, 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 integer. And this last one is kind of important because it illustrates that the integers are nested within the rational numbers. Because 3 over 1, as we can see, is just 3, an integer. And since we can take any integer and put it over 1, we can write any integer as a division of itself and 1, which means we can write any integer as a division of integers. That means all integers have to be rational numbers. Certainly that's not the only way of writing integers, because we could just as easily take 3 and also write it as, let's see if I can get this fairly close, 6 over 2. Or 12 over 4 would also be 3. Or let's pick something besides 3. How about, let's do 5. 35 over 7 would be 5. All of those are fractions of integers indicating their numbers are rational numbers. So every set we've looked at so far has been nested. The natural numbers are in the integers and the integers are in the rational numbers. Continuing on with rational numbers, here's a few words about decimal forms. The decimal forms of rational numbers have to be either finite length or infinite repeating. If you look at any rational number, any fraction of integers, you'll notice here 3/4, 0.75, that's a finite length decimal. 4/3 is 1 1/3, and from that you get an infinite repeating decimal. Here's a infinite repeating decimal that has a bit longer of a sequence, it's 6 digits. There's no really restriction on how long a repeating sequence must be. Your calculator will only show decimals out to 9 digits, so this is not really a perfect whether a number is rational or not. So you've just got to see if you can express the number as a fraction or not. And the rational numbers start to fill the holes between the integers on the number line, but not quite all of them. There's still quite a few numbers that don't really fit the definition of rational numbers. No matter how you express them, they can't be written as a fraction with an integer on the top. You can approximate them, but it's not going to be exact. From there, those types of numbers are called irrational numbers. And this is the first set of numbers we've looked at that's not nested. Irrational numbers literally means not rational. So these numbers have nothing in common with the rationals. Well, what's left? We've already looked at finite decimals. We've already looked at infinite repeating decimals. So probably the easiest way to describe these types of numbers is looking at infinite non-repeating decimals. And that's really the best description of irrational numbers we have, because they are difficult to express. I mean, think about it. You can't really express them as a decimal because there's an infinite number of digits, and you can't use a trick like the overbar you use on repeating decimals. But there are a lot of these, so what do we use to discuss them if we can't use our traditional numeric symbols? Well, we usually use special symbols. Most people are familiar with at least one irrational number. Pi. Pi is probably the most famous irrational number. It is an infinite non-repeating decimal. E we'll see later in the semester. Same thing for this ln symbol. That's a natural logarithm of 3. But this one we'll see very soon. Irreducible roots are irrational numbers. If you plug them into the calculator, a lot of them, even in the first 9 digits, you can tell they are not repeating. That's a very good source of irrational numbers, is irreducible roots. And coming to the end here, real numbers are just the set of all rational or irrational numbers. Once you collect those two sets together, we have a complete number line. Every single dot on the number line is a real number, represents a real number. There are no holes left. And sometimes it's called the real line instead of a number line because it is literally a visual representation of every real number. I hope you enjoyed the lesson. I'll talk to you again on the second lecture of this P2 series.